Good afternoon, children. Today we are going to start the second part on haloalkanes and haloarenes. So we have already discussed so many concepts, and today we are going to discuss some more concepts on haloalkanes and haloarenes. So let us begin without any further delay. Okay, so the first question is on your screen. Everyone pause the screen and try. So let's see what's given in this question. It's given here that CH3, CH2, CH2Br. So basically it's given propyl bromide to us, right? It's given propyl bromide. And its reaction with NaCN is given to us, and the product that is given, that is also given to us, right? So now the question here is, in which of the following solvent the reaction is going to be fastest? In which of the following solvent the reaction is going to be fastest? So some of the solvents are given to you here. Okay, these are your solvents. Now, in order to know that in which solvent the reaction is going to be fastest, we have to concentrate that what kind of reaction is this, whether it is SN1 reaction or whether it is SN2 reaction, right? So we have to think whether it is SN1 reaction or it is SN2 reaction. If it is SN1 reaction, the reaction will be fastest in case of polar protic solvent. Yes, Sharon? If it follows SN2 reaction, then it is going to be polar aprotic solvent. Yes, children. So polar protic solvent and polar aprotic solvent, right? Okay. So now we see that this is 1 degree halide. This is 1 degree halide. And looking at the order of reactivity, we know that in case of SN1 reaction, 3 degree greater than 2 degree greater than 1 degree is going to be a reactivity. Yes. Whereas in case of SN2 reaction, children, what is the order of reactivity? It is 1 degree greater than 2 degree greater than 3 degree, right? This is going to be your reactivity. Yes. Okay. So here this is 1 degree. So this is going to follow which reaction, children? Which reaction mechanism? It is going to follow SN2 mechanism. It is going to follow SN2 mechanism. As it is going to follow SN2 mechanism, so can I say that it is going to be the best in case of polar aprotic solvent? In case of polar aprotic solvent. So in which of the following do you see a polar aprotic solvent? We see that here this is polar protic, this is polar protic, and this is also polar protic. Only this one, children. N-dimethyl formamide, which is a DMF, that is your what? Polar aprotic solvent. So your answer is going to be option C. Your answer is going to be option C. Did everyone understand? Yes, I hope everyone would have understood. Okay. So with this, we'll move on to the next question and see. Yes. So next question on your screen. Everyone try. Okay, children. So the next question that has been asked to us here is, SN1 reaction on chiral centers, what happens? We are being talked about SN1 reaction, right? So children, as you know, in case of SN1 reaction, we have we have carbocation formation, right? And what is the shape of the carbocation, children? It is sp2 hybridized, hence it is having a planar shape. Means it is going to look something like this, right? Okay. So now, as this is like this, the tag can be from the front side, which will lead to retention. The attack can also be from the back side, leading to inversion of configuration. Yes, so as both are possible, so we say that this leads to racemization. This leads to racemization. Yes, so looking at the options, 100% retention and 100% inversion can be ruled out. Yes, so we are left with two things. One is 100% racemization, inversion more than retention leading to partial racemization. So what is this? So what happens actually, children, in case of your SN1 reaction? In case of your SN1 reaction, what happens in case of SN1 reaction is that the rate depends how shielded the front part is. How shielded the front part is. Okay, so more it is being shielded, then more is going to be your reactivity. Then more is going to be your reactivity, right? So if the front part is shielded, children, so obviously the inverted product is going to be more. The inverted product is going to be more, right? So can I say that the inversion is greater than retention here, right? Inversion is going to be greater than retention. So option 1 is going to be your correct answer. Option 1 is going to be the correct answer, right? Okay. So inversion more than retention leading to partial racemization. Okay. Yes. So next question on your screen, children. I'll be invisible for a moment so that you can see the screen properly. Yes. Okay. Try the question. Okay, children. So let's see what's given in the question here. I hope you all would have read the question. It's given here that what is the correct order of nucleophilic substitution of the following compounds with NaOH? So we are searching for a nucleophile, right? Nucleophilic substitution center. So it's initiated by a nucleophile, right? So nucleophile here is your OH minus. Yes, this is going to be your nucleophile. When it's a nucleophile, it is going to search for what kind of centers, children? It is going to look out for positive centers. It is going to look out for positive centers. So wherever you find maximum positivity or maximum electrophilicity, wherever you find maximum positivity or maximum electrophilicity, there your substitution is going to be maximum. There your substitution is going to be maximum. So can I say that where there are more electron withdrawing groups or stronger withdrawing groups, so there your positivity is going to be higher. There your positivity is going to be higher, and hence I can say that what, children, that wherever the positivity or the electrophilicity is higher, there your substitution is going to be higher. So as I can see in D, as you can see here, there is 1, 2 and 3 electron withdrawing groups, 3 EWG, right? Whereas in the third case, we are having only 1 EWG, right? In this case, OME is an electron releasing group, right? So this is ERG. This is a electron releasing group. Whereas this is neutral, like it doesn't have a electron withdrawing group or electron releasing group. So we are not considering the Cl for once, right? We are considering that this is chlorobenzene, and with that some group is attached to it, and with that some group is attached to it, right? So can I say here, children, can I say here that, what can I say here? So more the number of electron withdrawing groups, higher is the nucleophilic substitution. Higher is the nucleophilic substitution. So in case of D, we have the highest substitution, right? Because 3 electron withdrawing groups are present. Whereas after that we'll have C, because we at least have an electron withdrawing group here. We at least have an electron withdrawing group. But out of A and B, tell me, out of A and B, which is going to be more reactive? Obviously A is going to be more reactive. At least it doesn't have someone which is decreasing its electrophilicity, right? Okay, it's neutral, there's no group, that's okay. But in case of B, we are having electron releasing group. But in case of B, we are having electron releasing group. That's why, can I say that D is going to be the highest? So we can cancel option A and D, right? So now you see, between A and B there's a confusion, and we found out that A is going to be more and B is going to be your least reactive. Right? So option B is going to be your correct answer. Yes, option B is going to be your correct answer. Okay, and as you can see, this is a wrong option. Yes, this is not the answer. This is going to be your answer, children. Yes, this is going to be your answer. Yes, okay, so second one is going to be your answer. Just change it. This is not going to be your answer. Yes, I hope everyone understood this. Okay, let us move on to the next question. So what is the key concept that we drew from here? The key concept that we drew from here is that whenever there is a nucleophile, and you are searching for their reactivity, you have to see those centers which are more positive. Yes, okay, understood everyone? Yes, okay. Let us move on to the next question, children. Yes, so next question on your screen, pause and try. Okay, I hope by now you would have figured out that what the answer is. So let us see, children. Our question is given to us here that you're given RCH2Br plus I minus in the presence of acetone, and you got this HDME is a product and Br minus. Yes, that is a question being asked to us. And out of these, some statements are given to you, and you have to answer that which of the following is the correct statement, right? So let us look at the first statement. Let us look at all the statements. The solvent used in the reaction solvates the ions formed in the rate determining step. Okay, before that, let us look at the reaction again. So if you look at this one, this is 1 degree, children. Okay, so 1 degree, so this is going to follow your SN2 reaction. Right? Okay, now if you look at this reaction, can you identify, children, this is your Finkelstein reaction? Yes, this is your Finkelstein reaction. Now the question here is, the solvent used in this reaction solvates the ions formed in the redetermining step. Ions means it is talking about some sort of charged particles. Yes, so basically here it can talk about cation, but are we going to have some cations here? No, this is wrong, right? Why? Because children, this is following your SN2 reaction, and in SN2 reaction, we do not have any carbocations, right? We do not have any, so there is no talking about solvation, and we know that solvation, wherever there is solvation is directly proportional to your SN1 reaction, is proportional to SN1 reaction. When we talk about SN2, that much we are not concerned about the solvation. There is redetermining step. We are having only, it's a single step reaction. It's a single step reaction. That is what we are talking about in this. Br minus can act as a competing nucleophile. No, right? Because I minus is a stronger nucleophile, right? The reaction can occur in acetic acid also. No, this is Finkelstein reaction, and we know that here we are using acetone here. The transition state formed in the above reaction is less polar than the localized anion, right? So it is telling that this is a localized anion. It is saying that this transition state that is formed, it is less polar. Yes, obviously children, whatever the transition state you are going to get, that is going to be less polar. Yes, it is very unstable as well. That's why it directly gives you the product. It gives you the product, right? So which one is going to be your correct answer, children? Your answer is going to be option D. Your answer is going to be option D, right? Okay. So can we say that we understood this, that this is going to follow what kind of mechanism? SN2 mechanism. Yes, and we don't talk about solvents here. We are talking about anything that involves a transition state, because in SN2 we have transition state, and in SN1 we do not have any sort of transition state, right? Okay. Moving on to the next question, children. Okay, a good question. So use your brain and answer. Okay, children. So let us see what's given in this question. It's given here the correct order of melting point of dichlorobenzene. So we are given with three types of dichlorobenzenes, right? One is your ortho, another is your para, and one is your meta. Right, children? Okay. Now you would be wondering, how do we find out the correct order of melting point? We know that whenever the bond is very, very strong, when the bond or the lattice is very strong, in those cases we can see that the melting point is very high. The melting point is going to be very, very high. Now, as we can see that in case of this one, in case of this structure, it's very symmetrical. The lattice is very symmetrical. So can I say that this is a symmetrical lattice? Yes, this has a very symmetrical lattice. Because of symmetry, can I say that this one is going to have the highest boiling point? Sorry, highest melting point. Right? So wherever you see that para is there, so para is going to have the highest. Okay, para is going to have the highest. So second option, third option can be ruled out. Why, children? Because we see that in these options, the ortho is being given the highest one, right? So this much part is clear. Now discussing about the second part. Now we'll look at the dipole moment. We'll see mu. As you can see, there are angles here. There are angles here, right? So this is a smaller angle. This is a larger angle. And this mu, it depends upon the cos theta. It depends upon the cos theta, right? It depends upon the cos theta. Now, as the angle is minimum here, the angle is minimum here, cos theta, the theta is minimum. Yes, the theta is minimum in case of this. Yes, in case of this. Okay, so can I say the mu value is going to be maximum for ortho, right? So can I say that, but as compared to ortho, meta is going to be lesser. As compared to ortho, meta is going to be lesser. So can I say that the highest is para, the least is going to be meta? So definitely the second one is ortho. So can I say it's para greater than ortho greater than meta, right? So that is in option number 4. Option number 4 is going to be your correct answer, right? Okay. You could have told, or you could have asked, that in case of para there is a greater angle, but also there is symmetry. The symmetry is very much, yeah, the symmetry is very much. That's why we took into consideration that this is going to have the highest melting point. This is going to have the highest melting point, right? Okay, I hope this is clear. We learned 2 things from here about the melting point. We learned about the crystal lattice, okay, how strong or how symmetrical is the crystal lattice. We also learned about the dipole moment here, which depends upon the cos theta. Hence, in turn, it affects your melting point, right? Okay. Let's go to the next question. So next question on your screen. I haven't provided any option here. You need to think by yourself. Try, everyone. Okay. Okay, children. So here the question that is being asked to us is decreasing order towards SN1 reaction for the following compound. So whenever we talk about SN1 reaction, what is the first thing that comes into our mind is the stability of carbocation. Yes, stability of carbocation. That is what we are talking about here. Also, we talk about the ease of formation of carbocation, right? Ease of formation of carbocation. Yes, are these 2 things clear to all of you, that whenever we are going to talk about SN1 reaction, 2 things must cross our mind. First thing is the stability of carbocation and the ease of formation of carbocation, right? We know that carbocation has a planar structure with a positive charge in it, and after its formation, if it is stable, it is going to be formed easily, right? So I can say stability is directly proportional to formation, right? If something is not stable, it is not going to be formed, it will try to revert back, right? Okay, so what we are talking about here, we'll take all these, and we know that this is benzyl chloride. Everywhere we have benzyl chloride. This is CH2 group, right? This is CH2 group, and we know benzyl itself is a very stable carbocation, right? So if you are removing this from here, you are removing this. Okay, we are removing this. Okay, we'll remove this. I'll keep some, just a minute. Okay, so what I'm going to do is I'll cover this. Yes, so we'll remove this, all of these. So we are removing the Cl, children. Yes, we're removing the Cl from all of these. And after this, what are we left with in all these cases? Do we have CH2 plus here? Do we have CH2 plus here? We have CH2 plus in all these following, right? Okay. Now, as you can see, children, as you can see here, that these, it needs electrons to be stable, right? In all these cases, and in which of the following cases can you find electrons which is making it stable? Obviously, OMe is electron donating. OMe is electron donating, right? Okay, so OMe is going to have the highest reactivity here. Yes, this is going to have the highest reactivity. Then we know that Cl is electron withdrawing, it is deactivating, whereas here there is nothing. So then D. So B, then D. NO2, this is going to be the last one. This is going to be the last one because this is electron withdrawing. This is electron withdrawing. Right? I hope everyone understood this, that how are we going to approach this question. We have to first remove the leaving group, then we'll see the carbocation, then we'll look at their stability. Then we are going to look at their stability. So this is going to have the highest stability, highest. This is going to be the lowest. Yes. Okay. Yes. I hope everyone understood. And this is plus R, but what, children? This is minus I. So this is deactivating, right? Okay. So let us move on to the next question now. Yeah. So next question on your screen, and everyone try. Okay, children. So let us see. So what are we supposed to do in this question? We are supposed to match the list 1 with list 2, right? What are we going to do? We are going to match the list 1 with list 2. So basically, these are some common reactions. Yes. So I haven't given any options here so that you can do it by yourself. Okay. So let us analyze the first reaction. What is given? It is given one aryl halide is given to us and one alkyl halide is given to us. And what are we getting? We are getting alkyl arene, right? We are getting an alkyl arene, or we are getting methyl benzene here. Can anyone say what reaction is this? So when we are having one aryl and one alkyl group and we are combining them, that is nothing but your Wurtz-Fittig reaction. That is nothing but your Wurtz-Fittig reaction. So can I say that A is 2? Yeah. Can I say that A is going to be option 2? So we'll erase this. I hope everyone understood this. Now, talking about the next reaction that we have, we are taking two aryl halides, right? We are taking two aryl halides and we are fitting them. So can I say in presence of sodium? Okay, this is going to give you diphenyl. Yeah, this is going to give you diphenyl. It is going to give you diphenyl. Yes or no, children? So as it's give you diphenyl, so we know that this is going to be a Fittig reaction. So your B is going to be Fittig reaction. B is going to be Fittig reaction. Yes, I hope everyone understood this. Okay, let us look at the next reaction. What's given to us in the next reaction? Let us see. It's given something disonium salt. Yes, as we can see. And whenever there is disonium salt, without any doubt, we are going to say that this is what? Sandmeyer reaction, right? So this is your disonium salt in the presence of Cu2, Cl2. We know that this is definitely going to replace this entire thing, and this is going to give you Cl. And this whole set of reaction is what reaction, children? This is your Sandmeyer reaction. This is your Sandmeyer reaction. And we are left with no option, but the last one is going to be Finkelstein reaction. Last one is going to be Finkelstein reaction, which we have discussed a while ago as well, right? We have discussed it a while ago that whenever we are preparing alkyl halides, yes, alkyl halides from, sorry, alkyl iodides. When we are preparing alkyl iodides from bromides or chlorides in the presence of NaI, yes, in the presence of NaI, that is going to be what kind of reaction, children? That is going to be your Finkelstein reaction. That is going to be your Finkelstein reaction. So from here, you got an idea that you have to remember the name reactions. These are direct questions from the name reactions, right? Easy question. Yeah, very easy question. So as you can see from organic, you're getting very simplified and non-complicated questions. Okay. Yes. Okay. Moving on to the next question. Yeah. So next question on your screen, and everyone try. Okay, children. So let's see what this question is asking from us. This question is saying, identify the correct order for the given property of the following compound. So some order is given to us, yeah, and beside that we are given that some compounds and their orders are given, so we have to identify that which one is correct. Yes, so let us analyze each and everything here. So the first one is given, okay, and this is talking about boiling point. Okay, so when talking about boiling point, we know that boiling point is directly proportional to molar mass. Yes, boiling point is directly proportional to van der Waals force of attraction. Yes. Okay. Can we say that van der Waals force of attraction, molar mass, also strength of bond? Yes. Okay. So these are the things we need to keep in mind while talking about boiling points of normal compounds. We're not taking isomeric ones into consideration here. So if we see, there are two carbons here. Chlorine is common everywhere. So difference is in the number of carbons. So this is two carbons here. There are three carbons here. There are four carbons here. Definitely the mass of four carbons will add up to the mass of chlorine. Yeah. So definitely this is going to be the highest one. Again this, then this. So can I say that this point is correct? So A is correct. So wherever you don't find A, that is going to be wrong. So this is not going to be your answer definitely. Yes. So am I clear with the first question, first option? Yeah. So we are done with this part. We'll erase this. Moving to the next option. What's given to us here? We're talking about density here, children. Okay. So talking about density here, we know that density is equal to mass by volume. Density is equal to mass by volume. So density is directly proportional to mass. Density is directly proportional to mass. So wherever your mass is higher, wherever your mass is going to be higher, your density is going to be higher. So as we can see, the number of carbons here is 2. Here the number of carbon is 3. Here the number of carbon is 2. Right? But we see that here we have bromine, here we have chlorine, here we have iodine, here we have iodine. Right? So this is going to be the highest. Yeah, because this cannot match. Although it has 3 carbons, this is not going to match the mass of iodine. So this is correct. But there is a confusion between this both. Right? This both. Bromine should have been, bromine has a very high mass as compared to chlorine. Right? So we have fluorine, chlorine, bromine. So bromine has a very high mass as compared to the mass of one carbon. Right? So this should have been the order. This should have been come here and this should have come here. Right? So this B is wrong. B has to be eliminated. So wherever is B, you can eliminate that. So this is going to be eliminated. Yeah. So because B is wrong. Can I say this? Yes. So now let us erase this one. Now looking at option C. So what do we have? Again, we are talking about boiling points. Again, here the concept that is being used is your boiling point is directly proportional to molar mass. Yes, here only one bromine is there, here two bromine is there, here three bromines are there. In addition to that, we have carbons as well, two carbons as well. Okay, here we are having two carbons, here also we are having two carbons. So everywhere you have two carbons. But here you have 3 bromine, which adds up very much to the mass, So this is correct. This is correct. So both have A and C. Now the deciding point is between D and E. Right? So let us look at option D. Okay. So again, something about density is being talked here. Okay. Okay, so let us see here what is being talked about. Density again we know is mass by volume. So can I see that? Here how many carbons are there, children? 1, 2, 3. 1, 2, 3. Here we have bromine and iodine. Here it's only bromine. So can I say that this mass 1 is greater than this mass? So this should have come here and this should have gone here. Again there is something here also. Right? We have bromine and chlorine. Here we have bromine and iodine. So this is the highest one. This is going to have the highest one, but it is the lowest. This one is lowest. So can I say that D is wrong? So D is wrong. right? So we are left with only one option, that is option 2, and that is going to be your correct answer. That is going to be your correct answer, right? So option 2 is going to be your correct answer. Nevertheless, we are going to look at the last option as well, and again it is talking about boiling points, and here we'll see what is being done. Yeah, we'll erase this part. Okay, so now let us see, children, what is being talked about in this part. So here we have 1, 2, 3, 4, 4 carbons. Here we have 1, 2, 3, 4 carbons. Here also we have 1, 2, 3, 4 carbons. So we can see that number of carbon is same, number of chlorine is same. So can we say that here we are talking about isomeric haloalkanes? Yes, can we say that here we are talking about isomeric haloalkanes? And we know that in case of isomeric haloalkanes, when the surface area decreases, your boiling point is also going to decrease. So that's why, children, this one is going to have the lowest boiling point. Yes, or we can see that when the branching increases, when your branching increases, your boiling point is going to decrease. So the highest branching is in this case. Okay, highest branching. So as it has the highest branching, it is the lowest. Yes, I hope everyone understood this question very properly. I told you all the concepts of boiling point and density. Yes, okay. So let us look at the next question, children. Next question on your screen, and everyone try. Okay, children. So now again we are talking about nucleophilic aromatic substitution. Yes, now this is a very important one again. So we are talking about nucleophilic aromatic substitution. We know that this substitution is very difficult, right? Nucleophilic aromatic substitution is very difficult. And why is that? Because we know that if this is Cl, yes, this is creating a partial double bond character, right? We have a partial double bond character. Now in substitution, we have to break a bond and form a new bond. In substitution, we have to break a bond. We have to basically break this bond and replace this with OH. But as there is a partial double bond character, it is difficult to break. Right? That is one reason. Okay, that is one reason we know. What is the other reason we know? We know that it is nucleophilic substitution, right? So a nucleophile is approaching. So when a nucleophile is approaching, it needs what kind of centers? It needs positive centers. It's in need of what kind of centers, children? It's in need of positive centers. But if we look, here we had negative charge. Again, here we are going to have a negative charge. Again, here we are going to have a negative charge. So at ortho, meta and para. At what positions? At ortho, meta and para. Sorry, at ortho and para, we are having negative charges. We are having negative charges. Right? Okay. We are having negative charges. So as we are having negative charges, so can I say that, children, something that decreases the negative charges is going to increase the reactivity. Something that decreases the negative charges is going to increase your reactivity. Decreasing negative charges means taking away electrons. Yeah, taking away electrons. And who takes away your electrons, children? Electron withdrawing group, they take away electrons. Right? So as we can see here, this is going to be the most reactive because both at ortho and para, they are having electron withdrawing group. So this is the most reactive. These are almost equally reactive because they are having at ortho and para, but this is having at meta. This is having at meta, which has very less effect. Okay, because a negative charge is at ortho and para, but we are keeping something at meta. So this is going to cause very less effect, and as it is going to cause very less effect, then it is going to have the lowest rate of reactivity. So this is going to have the lowest rate of reactivity. Yes, children. So can I say, I'll erase all of this. So now can I say that this is going to have the lowest rate? Why? Because this is present at meta position. So this EWG will have least effect. Yes, children. Okay. Is this clear to everyone? Moving on to the next question. Now everybody will try this question. Yes. Try, everyone. Okay. So hydrolysis of an alkyl fluoride is a slow reaction, but in the presence of NaI, the rate of hydrolysis increases. So what is given here, children? It is telling that suppose we have RCl and we are making it react, right? Suppose you have NaBr, okay, and you're trying to get. Now it is saying that RCl you are having and you're having NaI, the reactivity is higher, means easily you get Ri. And what is the reason? Okay, so it is saying that this is the thing. Okay, so is this correct? Yes, this statement is correct. Okay, why is it correct? That we have to see. I minus is a good nucleophile as well as a good leaving group. Yes. So we can say that I minus will approach. This will leave easily and this will approach easily. This is a good nucleophile. So it is a good attacking agent and it is going to come and attack easily. So can I say that both A and R are true and R is the correct explanation of E, right? So your answer is going to be option C. So option C is going to be your correct answer. Now, next question on your screen. Okay, try children. Okay, children. So what is given here? We are given with this. And we are conducting a substitution experiment here. In one case, we have given AgCN and another case, we have given NaCN. This one, children, is covalent in nature. And this, as we know, it is ionic in nature. Ionic means it will give us Na plus and Cn minus. Here both Nc and N are available for bonding. But here only N is available. Why? Because this is a covalent bond and C won't be free. Okay. And here, as we know, carbon-carbon bond is more stable. So the attack will be from Cn. So here we are going to get what, children? Okay, we are going to get cyanide. Yeah, Cn. Here what we are going to get, children, in case of AgCN, we are going to get Nc. Right? So in case of this is A, so this is going to be a major product and this is going to be your major product here. Yes, I hope everyone understood this question. Yeah, is it clear? So next question on your screen. Yeah, try everyone. Okay, let me solve this for you, children. What is given here? Let us see. Yeah, so this is one alcohol that is given to you. Now, children, the first thing that is being given to you is H plus. So H plus is going to add where there are electrons. So can I H plus is going to add here, right? So when H plus will add here, can I say that this is going to become OH2 plus? Yeah, one of the electron pair of O is going to go and this is going to acquire OH2 plus. This one is a good leaving group. This one is a good leaving group. Yes. So can I say that it will go away? Now, as it goes away, there is going to be a carbocation formed here. Yeah. As this will go away, there's going to be a carbocation formed here. So this will go away. Yes. This is going to go away. So we are going to be left only with this much and a positive charge. So when you are left with this, we know that nearby we are having a double bond and this is going to cause ring formation here. Yes. So as you can see, so we'll have 1, 2, 3, 4, 5, a pentagon. Yes. Now this bond has come and attached here at this point. So wherever at what point it has attached. So at this point it has attached. Yeah. And when it comes and attaches here, it is going to have two branches here. So it's going to have two branches here. And at this point, these 2 points are going to be nearby points. Yeah, so here it is going to have two branches here. Yes, I hope everyone understood. After this, what are we doing? We are adding HBr. From this HBr, your Br minus is going to come and it's going to attach here, right? Your Br minus is going to come and it's going to attach here. So can I say that this is going to be your final major product? Yeah. Is it clear, children? Okay. So this was your last question, children, and here we are at the end of the chapter. These were the maximum concepts that you could learn in case of your haloalkanes and haloarenes. Okay. So in the next class, we are going to start with new chapter, probably alcohol, phenol, and ether. Okay. So until then, take care, children. Bye bye, and I'll see you in the next class.